Today we're going to talk about the gas laws. The gas laws are laws that tell us how gases behave under certain conditions. And there are several aspects of gases that you have to take into account when you're deciding how a gas is going to behave. And they include the pressure, the volume, the temperature, and the amount of gas that you have available. And the gas laws show the relationship between these various aspects of the gas. So the first of these gas laws is called Boyle's Law. And Boyle's Law simply states that if the temperature of a gas remains constant, then the volume and pressure of the gas are inversely proportional. So Boyle's Law, it takes into account what happens in a gas situation when you either increase or decrease the volume or increase or decrease the pressure, but keep the temperature constant. And that's a very important thing to remember. Now, when it says they're inversely proportional, that basically says that when one goes up, the other goes down. Or when one goes down, the other goes up. Now, mathematically, it's expressed like this. P1 V1 is equal to P2 V2. That is to say, the product of the pressure and the volume in the first state is equal to the product of the pressure and the volume in the second state. And obviously, if in the first state the pressure goes from a high value to a low value, then the volume will have to go from a low value to a high value for equality to remain. So here's a diagram that basically shows, and another mathematical way to show this is down at the bottom, is that the product of the pressure and the volume remain constant. And so that means that if you have two states, then the product of the pressure and the volume in the first state has to be equal to the product of the pressure and the volume in the second state. And it shows, using the kinetic theory, why this is the case. You'll notice in the first state you have a larger volume, a lower pressure, because the molecules are wider apart and they run into each other and into the sides of the container less often. You make the volume smaller, the molecules are shoved together in such a way that they have to run into each other and run into the walls more often, and therefore the pressure has to increase. This is just a graph of what we're just saying. If you start on the left upper part, which is a high pressure, low volume situation, as you lower the pressure, you see that the line comes down and the volume gets greater and greater, goes from left to right. And this is the sort of, when something is inversely proportional, the slope of this line is going to be negative. That is, it goes from top left to lower right. So let's look at a couple problems of Boyle's Law. A gas occupies 1.656 liters at 1 atmosphere. And 1 atmosphere is just a measure of pressure. What will be the volume of this gas when the pressure becomes 3 atmospheres? So how do we do this? Well, first of all, you write your formula down. P1 V1 is equal to P2 V2. And you can do this one of two ways. What I normally do is solve this equation for what I want to know. So it says, what is the volume in the second state? So I would solve this equation for V2. So if we divide both sides by P2, P1 V1 over P2. Now what's P1? Well, P1 is 1 atmosphere. And V1 is 1.56 liters. And P2 is 3 atmospheres. And then we put all these into this equation. So 1 times 1.56 divided by 3 is equal to V2, and V2 is going to equal 0.52, and there are three significant figures in all these, if you look at this, and so you put a 0 on the end of that, and this is in liters, and so this will also be in liters, so your label is liters. So the new volume is 0.520 liters. Looking at the second one, a tank of nitrogen has a volume of 14 liters. So V1 is equal to 14 liters and a pressure of 760 millimeters of mercury. So P1 is 760 millimeters of mercury. Find the volume of nitrogen when the pressure is changed to 400 millimeters of mercury while the temperature is held constant. So P2 is going to be 400 millimeters of mercury. And we have the same formula, P1 V1 is equal to P2 V2. And if you look at this, it says find the volume. So we're going to go for V2 again. So it's very much the same as the first problem, dividing both sides by P2. So if we put our numbers in, 760 times 14.0 divided by 400. I'm just trying to figure out an easy way to do this. If we divide this into that, we get 1 point, and that's going to be 336.9. So it's going to be 14 times 1.9. It's going to be 36. Excuse me. 12,014. This is a 0. So this is a 662. So the new V2, again, to three significant figures, is going to be 26.6 liters. Now there's a way you can check both of these problems, and I'm going to tell you about that right now. If you start out here, you say that the pressure here is going to go up, so the volume has to go down. So one check is your answer has to be less than what you started out with, because the volume has to go down. Similarly, here the pressure goes down, so the volume has to go up. So this number has to be greater than this number. Now another way to check it is you say, okay, you're starting out with 14 liters, and you're going to multiply that by a fraction. Since the pressure's going down, the volume has to go up, so you have to multiply it by a fraction that will increase the volume, and this fraction will increase the volume, and then you multiply that and see if you get the same answer, and you will get the same answer. But I recommend, as far as those are just double checks, use this formula when you do these problems so you don't get confused. The second law that we're going to talk about is called Charles' law. Charles' law states that if the pressure of a gas remains constant, the volume and the temperature are directly proportional. Now with Boyle's law, they were inversely proportional, and that meant when one went up, the other went down. But now if they're directly proportional, that means that when one goes up, the other goes up, if the pressure remains the same. Mathematically, well, first of all, I forgot to mention that. Whenever you do problems, the temperature must be in Kelvin scale. The most common mistake that students make, consistent mistake that students make, is they forget to change the temperature to Kelvin scale, which is why we went to all the trouble of showing you how to do that. Mathematically, it looks like this. V1 over T1 is equal to V2 over T2. And again, because it's directly proportional, it looks like this, as opposed to Boyle's law, which was inversely proportional, and it was P1 times V1. This is V1 divided by T1. And again, instead of the slope of the line being negative, the slope of the line is positive. You have with every increase in temperature, and notice the temperature is in Kelvin, the volume increases. The first problem states you have a 600 milliliters of air in a balloon at 20 degrees centigrade. What is the volume at 60 degrees centigrade? So let's write down, we have the volume. The first volume is 600 milliliters. The first temperature is 20 degrees centigrade, which if you add 273.15 to that, you get 293.15 degrees Kelvin. V2 is what you don't know, and T2 is now 60 degrees. So, and if you add 273 to that, you get 333.15 degrees Kelvin. And that's just 60 plus 273 plus 273.15. Now our formula was V1 over T1 is equal to V2 over T2. And we want V2, okay, so we cross multiply. So we have V1 times T2 is equal to T1 times V2. Solving for V2, we get V1 times T2 over T1, and then we put the numbers in. So we get 600 times 333.15 divided by 293.15. The answer will be to three significant figures, and we get an answer of 682, let me write that again, 682 milliliters. Three significant figures, because the temperature is in three significant figures. Let's do another one. A balloon has a volume of 2,500 milliliters. So V1 is equal to 2,500 milliliters. On a day when the temperature is 30 degrees centigrade. So it's 30 degrees centigrade plus 273 is going to be 303.15 degrees Kelvin. If the temperature at night falls to 10 degrees, so T2 is now 10 degrees, or 283.15 degrees Kelvin, then what's V2 if the pressure remains constant? And again, it looks very much the same as this, so I'm just going to write down V2 is equal to V1 T2 over T1. I'm not going to rewrite all this again. You can do that if you want. V2 now is going to equal 2,500 times, and T2 is 283.15 divided by 303.15. If we do this math, again, to three significant figures, it's going to be 2,340 milliliters. 2,340 milliliters. The actual answer on the calculator is 2335.065, but rounding up to three significant figures, that's the answer that you get. And it's because the temperatures are in three significant figures. I know when I added the conversion, I got five significant figures, but that you can't use the conversions significant figures. You have to use the measurements significant figures. And if you don't understand that, we'll talk about that in class.